information, the analysis of networks employing Zener diodes actually is quite similar to the analysis of semiconductor diodes. So that's mean in forward region here. In forward region, it start conducting around 0.7 volt. Okay, just like an ordinary silicon diode. But in this region, which is in the leakage region between 0 and breakdown here, okay, if you can notice from this curve, it has only a small reverse current. Okay, so the changes of currents is very small, and the characteristic drops actually almost vertical manner at a reverse bias potential, and at one point, this point, when we have this value is called as Vz. So Vz is the Zener voltage. Okay, so if you see from this curve, for currents less than IZK, which is IZK refer to Zener knee current, as VR increases, you can notice there is negligible change occurs in current. Okay, and here the breakdown start at a reverse current of IZK because of two reasons. The first one, the internal resistance of the Zener diode decreases, and the second one, current increases drastically but voltage remains almost constant. Okay, so for the next part is IZ. So IZ is a test current, which is refer to the current at which Zener breakdown voltage and equivalent internal impedance specification can be guaranteed. So if you see from here, currents higher than the test current result in slightly higher breakdown voltage, and then it will create a lower internal impedance. Okay, so next we move to next diagram, which is the same IV curve of a Zener diode. So if you look at this figure, we can notice when there is a change in Zener current, it will produce a small change in Zener voltage. So we use a simple equation, which is Ohm's law. So from Ohm's law, if we have a delta Iz for current axis, and we have a delta Vz at the voltage axis, so the ratio between the ratio of delta Vz to delta Iz, we call it as impedance. Okay, so this equation you can use to calculate the impedance of Zener diode. Okay, so ZZ actually is a small constant over the full range currents values. Therefore, if you see from this curve, we should avoid operating a Zener diode near the knee of the curve. Why? As I mentioned before, because the impedance changes is very obvious here, is dramatically changed in this area. So we should avoid to operate a Zener diode in this region. Okay, so next we move to next slide, in which I show you the schematic diagram of a Zener diode. Okay, so if you compare these two symbols, you can see the difference of the symbol. So the schematic symbol of a Zener diode is very similar to normal diode, but the difference is Zener diode, they have bent edges on the bar. Okay, so for semiconductor diode, the on state will support a current in the direction of the arrow in the same in the symbol. Okay, so but for Zener diode here, the direction of conduction is opposite to that of arrow in the symbol. So the Zener still can conduct electricity in forward direction like normal diode, but it also can conduct in the reverse direction with the condition the voltage applied is reversed and larger than the Zener breakdown, as I discussed in the previous slide. Okay, so the basic circuit with a Zener diode is like this. So from here they have a V in and we can measure the V out, and then there is a function of Zener which is requires that V in should be bigger than Vz. So there are a couple things we need to consider. The first one, sorry. The first one is the input voltage should be higher than the Zener voltage. And then the second fact is the resistor values must be chosen such that there is always current flowing through the Zener. Okay, so we will discuss about one example which is using Zener. Okay, let's say we have a simple Zener circuit as a voltage regulator. Okay, so given to us some information like this, and the maximum power of dissipation is 1 watt. Okay, in solving this kind of question, the first thing you should know is what is the meaning of these values. Okay, understand well what is the meaning of these values and how it this value is determined. Okay, so again, we will refer to IV curve of Zener diode in reverse region, reverse bias region. So you can see the value of where is the value IZK can be determined, and then we can have IZ test current, and also we have IZM. Okay, IZM is I current Zener maximum. All right. Can you see my pen? Okay. So IZM actually is the maximum current that can flow through the Zener diode. So that's mean when we have a Zener maximum, when we have a Zener maximum, maximum current for Zener diode, we also have PZM, which is maximum power dissipation at this particular region. Okay, so that's mean PZM power is a maximum power that the Zener can hold or can handle. Okay, so Vz is the value where the Zener can operate. And we have Iz, which is the test current, and we have Izk is the starting point for the knee voltage. And we have impedance. Okay, Zz, as I mentioned, we can calculate from the delta Vz and also delta Iz. So we already know from where this value is determined. Okay, so how to solve a problem? We use the same question, but the first part we want to calculate the V out. at IZK. So if you refer to the diagram, so V out we can measure at this particular point. All right. So how can we know the value of a voltage at these points? Okay, when we set V out at a value of IZK. Okay, so very simple. At IZK, V out, because that is the final destination of a voltage, so we will get the difference between the the total voltage that can flow. So they should overcome the voltage of Zener. So that means Zener should be deducted, remove part of delta IZ with ZZ. So we will have 15 volt minus with IZ minus IZK, because we want to know the test current and knee current. So this is the difference between these two parts. And then we have Z. Okay, so finally you plug in the values. Okay, the tricky part, normally students make mistake here because they don't know how to find delta IZ. Okay, again, you should refer how to get delta IZ. Okay, so next part is after we calculate these values, we will get V out as 14.76 volt. Okay, again, you have to refer the basic IV curve of Zener diode. First step, understand this profile. Okay. Second step, you identify where you can find the values that important in solving the Zener diode calculation. Okay, the second part, we want to calculate the V out at IZM. So what is the value of a voltage that come out at this particular point of current? Okay, as I mentioned before, IZM will involve with maximum power dissipation. So PD max is given as 1 watt, and using Ohm's law, very simple equation, we can have 0.667 for IZM. Very simple, right? Okay, so now we already know IZM value. Okay, because IZM value is not given in the text. And then from there, we can calculate the voltage out at this particular IZM value, which is 0.667 ampere. So here, if you see from the equation, there is a difference between these two equations. Okay, the first one, this one is after IZM. That means is a minimum. Okay, for that means this value should be lower than refer to the lower region of IZM. But IZM is a maximum. It should refer to the higher part of IZM. IZK is below part of IZK, the voltage at below part of IZK. IZM is above the part of the IZM part. Okay, that's why we put a plus here. So again, with the same equation from Ohm's law, we can calculate a V out at IZM as 15.7 volt. Okay, that is the at maximum part. So we can see the value at IZK is smaller, but for IZM is bigger. Okay, because IZM is the current is the condition where current received by the Zener diode is maximum. So that means the maximum current received, the higher value of voltage can be produced. Okay, next.
Doctor,
Yeah.
what is VZ? Is it the voltage across the diode? The
VZ
V.
is Zener. Here, VZ. Because it must overcome the voltage of Zener. If not, it cannot function, right?
Yeah. Yeah.
Mm. Is it clear?
Mm,
Which part?
because I just
Hmm?
not sure when you plus or minus the other voltage.
This one.
Mm, yeah.
Ah, this one at maximum we plus, at minimum at the lower we minus, because you see the position of IZK. Okay, we need to remove the voltage before it flow to the knee voltage. But for the plus, because it's over the VZ at maximum, that means the voltage supply here should be cannot exceed at higher current here. If you refer to this region, can you see my pen here? You should remove. But this one is on the top of IZ
Mm,
value.
okay.
Understand?
Yeah, yeah,
Okay. Can I move to next part?
yeah.
Okay, thank you. Any more question from others? Do you have any question? Is it you can follow my lecture or not? Huh? Okay, so I will proceed with a second with using the same example, but for the second question, in which we want to know the value of a resistance that we should use for this circuit. Okay, so in this question, actually we already said that voltage resistor is in the circuit is 15 ohm. Okay, so when we want to know the value of R that we should use in this circuit, that means they want us to calculate R for the maximum Zener current that occurs when there is no load. Okay, that means we remove the load from the circuit. Don't consider the load, okay, because we also do not know the value of load. Okay, so for this part, what is the value of R we should use? Okay, so very simple, because we still use Ohm's law, which is V in minus V out divided by current, because we want to know R. Okay, so I hope you understand. Okay, maybe some of you do not know what is Ohm's current. Okay, because in certain country they did not cover about the Ohm's current during their science syllabus. I don't know, because based on my experience. Okay, Ohm's law is V equals to IR. Okay, so you can manipulate this equation to get certain parameter. For example, like if you want to know I from the equation V equals to IR, you should have I equals to V R over V, something like that. Okay, so we use Ohm's law, and then because the maximum Zener current, then we already calculate the Zener current maximum, and then the total voltage in is referred to the voltage or power supply voltage, and then V out we calculate at IZM just now, and then with the value of IZM calculated in the first part, and then we know we will get the value of R equal to 124 ohms. Okay, so without load, that means this value R equals 124 ohm refer to the maximum resistance at maximum Zener current without load. Okay, so the next part, we want to determine the minimum value of R load. Okay, just now without load, now with a load. Okay, this refer to minimum load resistance, which is in other words, we understand that maximum load current, and the Zener current is minimum. So when Zener current minimum, we should know what is the total current in this circuit. Okay, so again, V in minus with V out, that is the total or resultant of V over 145, which is included in the circuit. And then we will get from this circuit, the value of total current should be 0.0637 ampere. Okay. But for the I load, okay, so we can have IT, which is I total minus with IZK. Okay, because that is the part of knee current. Okay, and then you will get the load, the current can flow or across the load is 0.06345 ampere. Okay, and then the last part is we want to calculate the resistance load, which is minimum. Okay, so how much they can receive the voltage and current. So RL equals to V out over IL. So IL we get from the I total minus IZK. Okay, so you can see the step how to find the value. Okay, so finally we will get R load for minimum is 233. Okay, so this value, which is a minimum, we can have 233 ohms. Okay, is it okay? Huh? Okay, so next part I will continue with application of Zener diode, because beside voltage regulation regulator application, Zener diode can be used in AC application to limit voltage swing of desired level to desired level. Okay, so this application is known as a clipper, and in some cases they call as limiter or amplitude selector or slicer in electronics term. And then if you notice that Zener limiter or Zener clipper, the diagram of the circuit is very simple, in which they have one diode of Zener, and then resistor, and then we have power supply. Okay, there are few approaches actually we can use Zener diode, because Zener diodes, once you change the direction, okay, the direction, the same thing, similar to a normal diode, once we change the direction of diode, it will change the direction of currents. Okay, that's that part we can manipulate with the diode arrangement. Okay, so this clipper circuit actually we can modify or shape of AC waveform. So we can use a bias voltage. That's mean the amount of the voltage form that is clipped off can be accurately controlled. Okay, so in this simple circuit like this, the input waveform of AC signal, I think because AC signal, you already familiar with this signal, which is we have V peak at positive voltage, and also we have negative V peak at the negative. We have V peak at negative voltage. Okay. So the same trend can be seen from the output signal without any slicer or without any limiter or clipper. So in this circuit, during the positive half waveform, the Zener diode is reverse bias, so that the waveform is clipped at the Zener voltage Vz. So clip, something like trim. Uh, so you set the cutoff of the voltage at a Zener voltage. Okay, so once it's flow through a Zener diode, you will notice in the output waveform, there is a square wave signal. Okay, so meaning that Zener clipper circuit, this circuit limits or cut off the waveform across them, and then in that case we can protect, or in the waveform shaping circuit we can use a Zener diode to model or to module the shape of waveform. Okay, so let's say if we wanted to clip the output waveform at 6 volt, for example. Okay, so we can use diode, Zener diode here, with a range of 6 volt. Okay, so if the output waveform exceeds the 6 volt limit, then the Zener diode will clip off the excess voltage from the input and produce a waveform with a flat top, but still keeping the output constant at 6 voltage, 6 volt. Okay, so meanwhile, during the negative half cycle, the Zener will have characteristic like a normal diode, which is 0.7 volt junction value. Okay, so that's mean at the negative part, the voltage will be clipped at negative 0.7 volt in the output waveform. Okay, so there are a few ways to to study the clipping characteristic, or the clipping clip circuit. So this during the first one is negative alternation. Okay, when the Zener acts as a forward bias diode, and then they can clip the voltage at the negative waveform as negative 0.7 uh, volt. Okay, and then the second part is when we change the direction. Okay, so what happens if we change the direction of a diode? Okay, so actually it depending on the orientation of the diode, the positive or negative region of the input, a small will be clicked off. Okay, so now we have a circuit with a Zener diode that connected in the opposite direction here. The same fundamental of Zener diode is referred when the Zener diode is connected to reverse polarity of the circuit. That's mean the negative peak is limited by the Zener action, and the positive voltage will be limits to 0.7 volt, and for the negative waveform, they will limited by the Zener voltage. Okay, so in other words, the shape of a waveform is vice versa to the first one, because of the um, orientation of the diode. the next part, we can connect back to back of Zener diode, which is we can use as AC regulator. So by using this systematic arrangement, we can clip the waveform between the positive, for example, like positive 6 voltage and the negative values of negative volt. Okay, so for example here, in other words, we will refer to the first Zener voltage, which is from here. At the positive waveform, it will clip at VZ1, and the second part at the negative waveform, it will clip the voltage using this orientation. Okay, so so then we move to another application of diode, which is light emitting diode. Okay, the optical diode is studied tremendously. I mean, the progress of the research is very remarkable, very good in the optoelectronics technology when they combine the optics and electronics part. Okay, but in this LED diode, light emitting diode, they will refer to the direct band gap. So we already know what is direct band gap. When there is a direct recombination can be seen between electrons and holes, and then they emit the energy in the form of light. Okay, this one I have asked in the tutorial 1, if I'm not mistaken. And then the LED colors actually depending on the material that we use to develop or to fabricate this device. For example, semiconductor materials such as gallium arsenide, gallium phosphide, arsenide phosphide, or gallium phosphide. Okay, and then uh, it will they will use the same concept of diode, simple diode, which is in forward bias. LED free electrons will move from higher energy levels to a lower energy levels as they fall into holes. And once the electron follow this route, they will give up an energy, and also they will produce light. Okay, there is a one phenomena, very important phenomena in LED, which is they involve with the movement or transportation of electron and holes, and it depends on semiconductor material, whether it's P-type and N-type. And I think you should know this because we already covered about PN junction. So in other words, we can say that LED only use a simple concept of PN junction. Okay, and free electrons in a conduction band. Okay, here with higher energy than holes in the valence band, and the difference in energy between electrons and holes will produce visible light. And when there is a recombination take place, the recombination electrons will release the energy in the form of photons. And then at the right side is the example of materials, semiconductor materials with their colors. So they will emit yellow radiation if we use gallium arsenide phosphide. And I think the most common with us is red radiation. Okay, because this one actually they use gallium arsenide to emit infrared radiation. And also if you go to electronic shop, you can see LED with green color. And then actually the material that they use to fabricate the LED in green color is gallium phosphide. Okay. Mm, yellow. Other colors, ultraviolet. I, I never see. I don't know. In the electronic shop, maybe you can have opportunity soon to explore in the electronic shop for the LED part. So for LED part, they use a current limiting a resistor. They use a very simple circuit to explain this, which is a nominal voltage drop of a 2.0 volt is normally used in DC analysis of circuit for LED. And also we use a very simple Ohm's law to get the IRS equals to Vs minus Vd over Rs. Okay. Vs is the power supply, and Vd is the voltage of diode, and R is the resistor in the circuit. And then you can calculate the current that can be produced from this simple circuit. Okay. So for example, I give you very simple example actually. We have one resistor, 500 ohm, and then we have Vd, but we want to know the value of IRS, and we use Ohm's law to calculate it, in which we get the resultant voltage, and then we divide by the resistor in the circuit. So finally you will get IRS equals to 16 milliampere. Okay, the next part is already 11. Oh, someone is coming. Okay, so the next application is optical diode, which is a photodiode. Okay, so photodiode, I think you know the concept, because it will. I think everyone know. I mean, up to this level, everyone will know what is photodiode, because we already covered during, school time, and also in the first year lab topic, which is photodiode. So uh, the photodiode also, they use a simple PN junction. Okay, so from here we have a photodiode, and this is the symbol of photodiode. So they use a simple PN junction, and once the light emit to them, something will happen to the holes and electrons in P and N junction. So optical diode, the same direction. I mean the same concept with a normal diode, but they are very sensitive to light. Okay, so for this type of photodiode, they will change light energy to the electrical energy, and how they do that. Okay, so in reverse bias, okay, once okay, if we supply the voltage of the power supply to this PN junction, okay, so negative terminal go to P. P contains a lot of holes, okay, and then the positive terminal attached to N, and N have a lot of electrons. Okay, so I think you should know what will happen, because they have opposite charge, okay, with the power supply and the majority carrier in PE and also in N. So the depletion region will be wider. Okay, so next, when the depletion region wider, we shine the light. Okay, then they will generate holes, electron pairs. Okay, and then they will start to move to opposite side. And then what will happen? The holes move to anode, and the electron will move to cathode. Okay, so lastly, for the photodiode, this is the characteristic of a photodiode, in which you can see we record the IV curve at the reverse bias region. That's mean under the dark current. Okay. And then the operation of a photodiode is limited or restricted to the reverse bias region. That's why the results of the photodiode is recorded in reverse bias voltage. And also, because they only operate during the reverse bias mode, then they will this photodiode will convert the energy into the electrical energy. And then when the ordinary diode is reverse bias, the reverse current start to increase with the reverse voltage. Okay, this one is a biasing arrangement for the photodiode. They operates in two modes, which is photoconductive and photovoltaic. So photovoltaic, in simple words, is solar cell. Okay. So for photo conductive, okay, the explanation is like this: when a photodiode operates in reverse bias mode, it only allow this function can be carried out. And then in this current flowing in diode varies linearly with the intensity of light incident, because light, they can influence the movement of holes and electrons, and also holes and electron recombination. And in photovoltaic, when the diode is operate without reverse bias, it is said to be operated in photovoltaic mode. And when the reverse bias is removed, the charge carrier swap across the junction, and barrier potential is negative on the N side and P side. Okay, and then the next part is a transistor. This topic is quite big compared to photodiodes and also limiter and Zener diode, because transistor, when you see trans and sister, okay, transfer, sister come from the resistor. Okay, so it is transferred resistance device, which is they capable to give us the value of current gain, and also voltage gain, and lastly is a signal power gain. Okay, there are few types actually of transistor, which is the first one is bipolar junction transistor, and we have field effect transistor FET. And also for junction, this one bipolar junction transistor, they have um two configuration. The first one is PNP. That's mean P N is sandwiched between two P's, two P junction. Okay, and the second one, the arrangement we can do is P is sandwiched in between two N type materials. Okay, so we look at the field effect transistor. The field effect transistor, this one, FET. Okay, FET, we can classify into two groups, which is the first one is metal oxide semiconductor FET, which is we call MOSFET. And the second one is junction FET, JFET. Okay, for MOSFET, we can group them into two types, which is the first one, N channel. Okay, that means the majority carrier is N, and P channel in the MOSFET. So if you read about this topic, you will find about NMOS and PMOS. Okay, for JFET, they also have two FET. Okay, the first one is PN JFET, and the second one's metal semiconductor field effect transistor MESFET. So here they have metal oxide for MOSFET. Okay, metal oxide. That means the metal in the oxide form. So what is the example of metal oxide? Can anyone answer? What is the example? Contoh metal oxide. Potassium oxide.
Aluminium oxide.
Aluminium oxide. Okay. Aluminium oxide, metal oxide. We will have, for example, commonly used, we can use, sorry, nickel oxide. Okay. We have cobalt oxide. Cobalt oxide, CO2O4. Or we have, CO2O, or we can have CO3O4. Okay, so the field is very broad, okay, but very interesting metal oxide semiconductor. And also a junction field effect transistor is metal. So they couple metal and semiconductor. So semiconductor, for example, like gallium arsenide, whatever, and then they couple with metal. Maybe they will use, in some cases, they will use orium, I mean metal, or platinum, okay, or silver. So that is MESFET. Okay, so you can explore this fact during your FYP. Okay, or maybe in during, I don't know, I'm not so sure whether in second year lab, which is applied lab, they have this kind of JFET, but I'm pretty sure photodiodes is covered. Okay, so our topic for basic electronics SIF 1005, we will focus on BJT. So I will make it clear, because we only cover the DC part of BJT. Okay, so when you move to the next level, which is electronics 2, you will study about AC part of BJT. Okay, so be clear that we only cover about DC part, which is quite simple compared to AC part. Okay, so transistor, they have three layers semiconductor device, which is I showed just now, which is we have NPN or PNP. And then this condition, this cache diagram is at unbiased NPN transistor. That means without any connection or polarity, or we did not connect this structure to any power supply. Okay, so we have N. I just want to explain that. Reminds you that N, we have majority is electron, and we have P, we have majority holes, and also the same thing. But for NPN, so the top layer is called collector. Okay, and the base, the second layer is base, and the third layer, the bottom layer is, the most bottom layer is emitter. Okay, so from the label itself, I think you should know what is collector. Okay, without knowing yet, I mean deeper in the function. And base, and also we have emitter. So once collect, one layer is collecting, one layer supporting, and the last layer they will emit the energy in terms of electricity. Okay, so this one we can because we already studied about PN junction, so you can see that in these two layer, between these two layer, there will be a depletion layer. Okay, so another part between this junction, which is P and N, we will have depletion layer. So in other words, you should know what is depletion layer first, and then how it influenced by the polarity of P and N junction. Okay, so this one we already discussed before this, which is before N apa MCO, and then the widen, I mean how they can get widens, how they can shrink the layer. It depends on the polarity of NPN junction. Okay, so the symbol of transistor we can write like this, which is we have NPN, and then we have C, B, and E, and this is the arrangement of the junction transformed into the symbol. Okay, so I think you know how the reaction ataupun behavior of the free electrons and the holes without any enforcement from the current. Okay, to be a good BJT, we need to have we need to have very thin base. Why? Just now already mentioned that base is something like a layer that support this back to back PNP, because they sandwich. Base is sandwiched in between of two identical semiconductor material. Okay, so in this slide, in this slide, we have PNP just now in the first slide is NPN. Okay, don't get confused. And why I use this example? Because I think that is your part to understand the concept of NPN and PNP. Okay, so I will cover maybe in one slide PNP. I will not cover PNP and NPN in one slide. Okay, so be careful or watch out. I mean, carefully the diagram or the configuration of transistor. Okay, so don't get confused. Okay, so this one is PNP again. The position of terminal is the same, which is we have emitter, base, and collector. And the crucial part is this and this. Okay, but before that, I will explain what is emitter, which is normally they have a heavily doped region of P. If N, that means they will heavily dope with electron. Okay, what is the purpose of this emitter? Because from the word they want to emit, so that means they will inject the carrier into the base thin layer, and then base layer, because we need to have very thin, right? Very thin layer. That means this region should be very lightly doped for N region. And what is its function? uh, it will pass emitter injected carriers. Okay, emitter pass the carriers to base, and then base will let them, flow to the collector with minimal recombination. If high recombination, that means the BJT is not working very well. Okay, because the electricity, the current, is depend on the number of carrier that pass through to the collector. So what is the function of collector? Okay, so because collector, before it receive main carrier from N, from the base, it has already have their own carrier. Okay, so once population of charge carrier enter or pass through from base to collector, this collector region will have a larger number of carrier, and then normally P or the collector layer will be thicker compared to layer of emitter. Okay, and then why? Because here, because they want to accumulate a lot of charge carrier. As I mentioned before, collector already have their own populations. Okay, once base allow another population of carrier to enter to the P, the second P. So that's why we need to build P or use thicker P, second P as collector. Okay, this is the same thing, which is emitter junction base, emitter base and collector. Okay, but here we want to know there is a emitter base junction. Okay, so this one we have NPN. Okay, just now I have PMP. Before that I have NPN. Okay, pening kan? Okay, this one is NPN. So the cross section of a transistor for NPN, the first thing we want to know about emitter base junction. Emitter N, base P. Okay. N, they have a lot of electron. P, they have a lot of holes. Okay. The junction in this in the between of these two layer, and then anode base will be as anode, and emitter will serve as cathode. Okay, so a majority of current will enters the collector terminal across the base resistor base region, which is originated from the emitter terminal. Okay, so here for the emitter base junction, if you can see, actually it is NP junction. Okay, for this configuration. So the next part, we have another PN junction, which is a collector and base junction. Okay, so that one is another PN junction. Just now for the EBJ is N and P. Okay, so that's mean the characteristic of the depletion layer for these two junctions is different. Okay, the junction between N collector and P collector, and then anode will be base and the cathode will be collector, and then the collector will receive the charge carrier, which is passed through from the base. Okay, so you have to identify the EBJ and CBJ, identify the configuration of CBJ and EBJ, and also understand what will happen once we change the polarity of the junction. Okay, so the next part, is I want to show how the influence of NPN junction. Okay, so we will discuss the essential reverse bias PN junction, and also you should know what is the behavior of electrons and holes for the PN junction. Okay, so there are two N type regions here and one P type region, which is sandwiched in between of N and P. Okay, so again, the first N type is called emitter. This layer is heavily doped, and they can accept a number of they will have a number of free electrons, which is serve as a majority carrier, which is quite large here. Okay, the middle p type is base, which is lightly doped, so the number of holes, which is a majority carrier in this layer, is quite small, and the base diffuse in between the wider emitter and collector region. But the base is quite thin compared to the outer emitter and collector region. So the second N-type region, okay, actually for this collector N-type is moderately doped, but the size of this region is the largest among the regions. Okay, so that's mean when they moderately dope, the number of free electrons in this layer is not as much as in the emitter region. Okay, because collector will receive the what we call charge carrier later after they pass through from the base. Okay, so now we will connect this BJT transistor to a battery. Okay, so look at this diagram. The negative terminal of the battery will connected to emitter. Okay, here negative to N. Okay, remember that N, they have a lot of electrons, free electrons. Okay, so hence emitter, this one will create emitter base junction, and then they will become forward bias, right? And the base collector junction will be as reverse bias. Okay, because this one attached to positive terminal of the battery. Okay, so that's mean for this configuration, no current will be flowed through this BJT. Okay, and then we already know that the emitter is is a heavily doped. Therefore, the concentration of majority carriers, which is free electrons, in this region is very high, and then because of this polarity, the current cannot be flowed. Okay, so this junction this mark region is the depletion region between the N and P and P and N. So we can see once we connect this circle, this junction to positive and negative terminal of battery, the depletion region will increase. And now we can label the voltage applied between the collector and emitter as VCE. So C is collector, E is emitter. So the voltage between collector and emitter is labeled as a VCE. And then this entire voltage applied between collector and emitter is dropped at two places, okay, which is C and E. Okay, so now one is at the forward barrier potential across the emitter base junction. We call it as a VBE. Okay, and VBE actually we know the barrier of the voltage is this one is about 0.7 volt for silicon made transistor. And then secondly, for the applied voltage drop, we can found at the reverse barrier across the base and collector junction, which is VCB. Okay, so now for this configuration, we can write VCE equal to VCB plus VBE. Okay, is it okay? So VCE is the total voltage from terminal emitter and collector. So VCB refer to the voltage at collector and base here. And this one, VBE, is voltage between emitter and base. Okay, so the total voltage across these two regions will result or will give to the value of the voltage of VCE. Okay, and then we can rearrange this equation. We can write or include the value of silicon diode voltage, knee voltage, which is VCE equal to VCB plus 0.7 volt. That's mean none of the collector voltage can overcome the forward barrier potential. Hence, none of the free electrons in the emitter region can cross the forward barrier potential and transported to base. Okay, so at this point, the BJT will behave as on switch. Okay, now let's see what happen if we supply. Okay, if we put or apply a second voltage source to this circuit. Okay, so from this circuit, okay, now I want to attach extra potential voltage supply at this particular layer, which is to the base. Okay, so this circuit we can simplify like this. Okay, and a positive terminal of a second voltage source is connected to the base of a BJT, and the negative will connect to the negative terminal of first voltage supply. So the scenario is totally changed, and in this situation, the base emitter junction gets forward voltage and able to overcome the forward potential barrier. If we increase the voltage between base and emitter, here we increase the voltage of the second supplier. What happened is when reach about 0.7 volt for VEB, okay, the free electrons start to cross. Okay, so this is the original condition. Once we attach second voltage to here, That's mean we try to make it this one as positive, right? So this one, the base have a lot of, I mean, the majority carrier is holes, so the electron will be attracted to the base. Okay, so when reach about 0.7 volt, the free electrons start to across the emitter base junction. High number of majority carriers of free electrons in the emitter will be cross the junction and go to the base region where they get very few numbers of holes to recombine. Okay, so now we will have IB enter to the base, and then they will, once the electron move in this loop, they will have current flow to the base. Okay. Oh, sorry. So for the current, we can write IE equals to IB plus IC. Okay, so IB plus IC will give the total current from IE. Okay, that's mean we can say that the total current accumulated across the IE will be equal to total current, the sum of current base and collector. Okay, so this is the symbol of BJT. You already know this one because I already showed in the previous slide. And from this diagram, we can summarize that IE equals to IB. And this one also we can explain from this diagram why IE equals to IB plus IC. And we know to write the equation for the voltage for 3 layers, which is VEC equals to VEB plus VBC. Okay, so for NPN, okay, now I want to highlight one thing, which is IE, I mean for the current, even configuration NPN or PNP, the arrangement or the equation is the same. Okay, the current, but the voltage notation for NPN and PNP is different because they NPN is N, it depends on the CE, for example, collector and emitter, that's mean end to end, right? So but in PNP, the collector and emitter is P to P. So the notation is slightly different, which is in NPN, the equation is VEC equals to VBE minus VBC. But for PNP is VEC equals to VEB minus VCE. Okay, any question? So up to now, for the mathematical part for BJT, the first one, we know the IE equals to IC plus IB, and the voltage gain of the beta is we can calculate from IC over IB, and from this equation later, we can do some derivation here to get alpha, and then IE equals to beta plus 1 IB, which is equivalent to IC. Okay, so how to show the relationship beta and alpha later? We need to know what is the expression for the current gain. Okay, so it depends on the configuration of current. Okay, and then beta current gain we can get as IC over IB. This one, no matter what kind of configuration, it will be the same. Okay, so here is the relationship between beta and alpha. Actually, I want to show in which we can derive or to show the derivation of alpha and beta. Kenapa dah pukul 12 ah? Okay, so equivalent hybrid parameter HFE is equal to beta BDC, and alpha, which is represent the total fraction of the emitter current contributed by the carrier injected into the base and reaching to the collector. So alpha DC is equal to IC over IE. Okay, so from this one, both are referred to the IC for the top value, and for the bottom value, they change only IB or IE. So that's mean we can correlates between beta and alpha by doing this simple derivation. Okay. Uh, and from this equation, we can have that alpha equals to beta over beta plus 1, and beta equals to alpha 1 minus alpha. So these two equation, alpha and beta, actually we derive from a very simple equation. You just substitute these two equation, and then get the alpha and beta equation. Okay, so lastly is the mode of operation of BJT. Actually, they have four modes, which is the first one is saturation, active region, breakdown, and lastly off. Okay, so off, that means the IB value is below than 0. Okay, the active region, normally we focus on active region and saturation region. So the saturation region is a potential where the potential barrier of the junction cancel each other out, causing the virtual short. That means there is a lot of charge carrier here. That's why they saturated there, and you can see that the value of voltage happen at a quite low. And after that, this region, we will get the active region, which is this one is very important mode operation for BJT, and then central to the amplification operation. And then normally the region of active region is almost flat. Okay, so lastly is the breakdown region when the BJT is not well functioned. And then the cutoff region, the current which is reduced to 0, and then it will behave like open switch. Okay, so here is the IV curve of BJT. Okay, so in other words, this one is the output characteristic of transistor. Okay, so you can see that we have a saturation region here, which is where the rapid increase of current when you change the voltage, and then after this period, they will almost flat region. This one is very active. That's mean they will increase the current slightly. Slightly, sikit-sikit kan. And then at this region is not function lah, because it's cut off region where the IB there is below than 0. That's mean there is no current flow through the base. So when there is no current flow to the base, so it cannot uh, push the carrier to the emitter. So there is no current flow into the BJT. Okay, this one, the explanation of how saturation happen, which is IB bigger than 0, and it start at VCE equals to 0. And then this happen when the BE and BC junction are forward bias, because when forward bias, both junction is forward bias, so there are a lot of charge carriers starts to move. Okay, and then the clue is both EBJ and CBJ is in forward bias. Okay, so that's why you can see the current very high, but the change in the voltage is very small. Okay, So the second part is the active or linear region, which is almost flat. This region we can obtain when we have a base collector junction. Okay, CBJ reverse bias, and the transistor is inactive. And then this curve actually as shown in this diagram, which is between B and C points. And then in active region, we can calculate IC equals to BDC over IB. Times with IB. And then as I mentioned before, that IC, the collector current increase very slightly as much as VCE increases. Okay, so lastly is NPN, which is at the region of breakdown. Okay, so after breakdown, which is the part of the curve to the right of point C, IC increase dramatically, and the transistor never be operated in this breakdown. Okay, I show you the difference between IC versus VCE for NPN and PMP. The shape is totally the same. Okay, whatever the configuration is, but the label, this is what we keep doing as a mistake, which is VCE and VEC refer to the PMP and NPN mode. And then this is the summary of a BJT operation mode, in which in active region, collector base junction is in reverse bias, but the BEJ in forward bias. And the characteristic, that's mean IC, we can calculate as beta IB. So beta normally the value is like 50, 100. It will give in, given in the text in the question. And for the saturation, we can have IC equals to I saturation. And how to get saturation? CBJ is forward and EBJ also in forward. So both are in forward condition. Okay. And then I just want to remind you that IC equals to beta IB only we can use during the active region. And for the for the cutoff region, it is both junctions are reverse. That's mean IC equals to IB equals to 0. So once there is no current at IB, IC also don't have current, and IE also 0 current. Okay. So okay. And then lastly, BJT we can discuss into three modes of three configurations. Okay, this one they will use as amplifier. So we have a common base configuration, common emitter configuration, and lastly is common collector. So what is the meaning of common base? So common base. Okay, I give you one clue that when they say common base, that means base is common for the input and for the output. In other words, base become a reference terminal to measure the voltage out from the output and out from the input. And go into the input. Okay. So the same thing for emitter. Emitter will be a common terminal for the output loop and the input loop. Okay, we look at the CB, which is common base, which is base is common. That means it become a reference terminal to the input and the output circuit. Actually, output loops. Okay, so this one output input circuit or loop, and this one is output loop. Okay, so this mode is referred as a ground-based configuration, and also you can redraw this basic circuit with the grounds like this. So don't get confused, because in some books or in some source reference, they will use a basic circuit, but actually it's the same. Only if you use circuit with ground, maybe some of you will get confused to understand the current flow. Okay, but basically it will refer back to the NPN or emitter base terminal. Okay, so for the CB configuration, there are two sets of characteristic, which is the first one is input characteristic, like this. Input characteristic means the behavior of current in this loop. Okay, and the output characteristic means the behavior at the output loops. Okay, the input characteristic actually describe the relationship between input current, which is IE, and the voltage input, which is VBE. Okay, so you can see it is a forward bias characteristic, right? And for the output characteristic, it will describe the relationship between the output IC and the VCB. Okay, and then you can see that this one, as I discussed before, where we can notice saturation region and active region, in which in active region you can calculate IC equals to IB beta. And for the current gain, we can use a normal equation, which is applies to all. And then it will change with, you can see that in this configuration, IC depends on the IE current, on the current of IE. So once it change, okay, the VCB or the IC level will be changed. Okay. And lastly, okay, there is a early effect, which is due to the forward bias and the base emitter junction. Again, you should know that there is a forward bias and also reverse bias. So the width, when we applies to these rules, that means it will involve with the depletion region, which is referred to the BEJ or CBJ. And then the early effect, it refer to depletion regions, which can penetrate more into the base region and less into the collector because of reverse and bias, reverse and forward bias of CBJ and EBJ. And then this depends on the base width on the output of VCB, which is known as the early effect. Okay, that's all for today. Any question? Oops. Huh? No question.
No.
Siapa baru masuk pintu? No question? Can you follow? Maybe can you follow my lecture? Is it too fast? I try not too fast, but okay. I will be frank to you. Frankly speaking, that this topic I never skip in final exam. At the end a bit fast because already 11:45 that time. That's why a little bit sorry. Okay, because you need to understand the actually, yeah, I should explain in detail the concept of reverse bias, or but the reverse bias and forward bias. But I think we already discussed this diffusion region, forward bias, reverse bias many times, right? Before the MCO. And also the trick is that first understand the depletion region. Okay, no, the first you should understand the content of a majority carrier. Okay, who is the majority carrier in P and N? We already know that. And how it react when we change the polarity, and how they control how we can control the depletion region. Okay, that is the basic clue lah for to understand the behavior of BJT. Okay, and then the second step, at the cross section, okay, or the simple configuration of BJT, you understand where is the depletion region uh, can be identified. Okay, for example, like this. Okay, when we have N, B, and okay, here. So N and P depletion region is smaller or thicker, thinner than the depletion region at the base and collector. So try to manipulate this condition or this phenomena by changing the polarity of the battery here. Okay. And number two, you change the you change the configuration, which is P and P. So from there, if you understand that, I think you will have no problem in question solving. Okay, I already uploaded the lecture notes in the week 9 activity, so do check. Yeah. Okay, any question, I encourage you to discuss in the group, so that I don't need to respond to the same question for many times. Okay, I really appreciate if you can discuss. No, nothing to worry. Okay, nothing to shy, because we want to share the knowledge. Okay. Okay, that's all for today. I have tried my best to deliver the content to you. Okay, so the next part, the next lecture, we will discuss about the DC analysis of BJT. Okay, so the analysis of BJT is something like this. No, this one already. Yeah. Okay, it's something like this, in which how to get uh, the how to solve the loop, the equation, okay, and then how to derive certain things and load lines equation. Okay, something like this. Okay, so before we go to more deeper, you still have time to understand. You need to understand the concept as I discuss here. Okay, because next part will be more equation. Okay, something like that. So, and then so it's quite difficult if you do not understand why suddenly IB equals to 0, something like that. And so in the equation, when we go to the, to solve the calculation, this one will blocks you to, to stop you to understand more. In the lecture. Okay. Okay, that's all for today. I hope you enjoy my class because I have tried my best. Actually, I want to record the lecture, but I already tried for 2 days, day and night. But I think my voice not very good and my my tone. I afraid that you think that singa betina di dalam lecture, something like that. I try to slow down my volume but can't. I don't know why. Maybe my voice not very good. Okay, but if you don't mind with um the condition of the recorded lecture, I can upload to you. But definitely it's not nice lah. It's not nice like other people, when they record very I see that very nice to hear, but maybe their voice are very 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 good. That is me actually because I don't know lah, my voice may be too loud. I don't know how to control. Maybe I should put some amplifier to control the signal. Okay. Do you want me to record the lecture? Or just enough with this lecture? If you want, I will try to I will try. 2 days until 3 o'clock in the morning like a ew. Then I really do not understand why people want to be a YouTuber, talk too much, I don't know, editing, etc. Is a lot of time. Record. Okay? So don't laugh at me, yeah. Sometimes my voice very like begging, Aduh. Okay, that's all for today. I already try my best to deliver the lecture. I hope you enjoy. I really hope that all of you score the subject. And I think after Raya, in June, week 10, you start to discuss regularly with me, okay, in the group. So I will help you to the best of my level. Okay. Okay, that's all for today. Thank you. And don't forget to click the attendance.